Hello all, welcome to video on section 3.3, determinants as area or volume. And a quick note that we skipped the very first part of the section on Cramer's rule. So we'll jump right into theorem 3.9. If A is a 2x2 matrix, the area of the parallelogram determined by the columns of A is the determinant, the absolute value of the determinant. And similarly, in 3 dimensions and actually in higher dimensions too, if you're interested in higher dimensional versions of volume. So let's first talk about what do I mean by the area determined by the parallelograms or by the columns of A, right? If we've got R2 right here, our x1 axis or x2 axis, the columns of A, so maybe A is given by A1, A2. You get these two vectors, A1, let's say, and A2. And this determines a parallelogram, right? Just by sort of finishing the thought of being like, well, we can go over like this and go over like that. So we're saying this area is actually the same as the determinant of the matrix, the absolute value of the determinant, rather. Okay, so let's give a quick sketch. Well, sort of a longish sketch, but we'll still give a sketch of why this is the case. Yeah, so let's first do the easiest possible case and check that it works out, and then try and reduce the easy case. So yeah, easy case. So if A is equal to a diagonal matrix, A0, 0, D, then what? Then the determinant of A is just AD. And sure enough, this means that our first vector is on the x1 axis, and this means that the second vector is on the x2 axis. So you get a rectangle, right? And sure enough, the area of a rectangle, there's this is not A, this is the vector A0. And here we've got the vector, say 0D. And sure enough, the parallelogram that these two define is actually a rectangle. And the area of the rectangle is AD, so we haven't lied. So this is the area of the parallelogram determined by the columns of A. Okay. And so then next we need to do the reduction to the simple case. So what? So we're done. If we can change every 2x2 matrix into a diagonal matrix using steps that don't change the determinant, don't change the absolute value of the determinant. So we're done if we can modify any 2x2 matrix into a diagonal form such that these modifications do not change the absolute value of the determinant of A. Okay, but the absolute value of the determinant we know is unchanged by swapping rows, because picking up a minus sign doesn't change the absolute value of the determinant, and it's unchanged by row reduction and column reduction. So in fact, that's it. Yeah, so then we know, the absolute value of the determinant of A is unchanged by interchanging rows or by row reduction or by column reduction, which is just row operations only for columns. I don't think we've explicitly talked about column reduction, but but certainly the determinant doesn't distinguish between rows and columns. Yeah, so the claim is that this is actually enough. The claim this is enough to change, to make any 2x2 matrix diagonal. Okay, and then similarly, exchanging columns of a matrix doesn't impact the parallelogram at all. So column, oops. So column or row interchange. Interchange. It's not change the parallelogram. So the area is preserved. And then row operations or row reduction. This is the less obvious one. The row reduction amounts to or corresponds to changing just basically the angle of the parallelogram. And that does, and then a little bit of Euclidean geometry shows that actually, if you change that angle of the parallelogram but not the height, you don't change the area. Corresponds to changing the angle of the parallelogram. But not the height. And a little geometry shows you that the area isn't changed by this. Oops. Area remains the same. Okay. So as always, the details are in the textbook. We're just trying to give you some idea of why this ought to be true. So let's do an example using this theorem. So yeah, someone comes at us and they say, find the area of this parallelogram. And you think to yourself, well, how am I going to get out of this one? But you're in good shape. Let's do a little crude plane over here and see if we can't figure out what's happening. We've got 1, 2, 3, 4. 1, 2, 3, 4. This is our x2 axis. Okay, and our parallelogram uses 1, 1, 3, 2, 2, 3, and 4, 4. Okay, that's not a bad looking parallelogram. So boop, 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 boop. This is the thing we want. And the first trick we need to play is, okay, well, what we'd actually like is for these two vectors to give us a matrix, and right now they don't. Because they aren't vectors, because they're just lines in space. But if we translate everything, left one and down one, then we get a matrix. Yeah, we get, I'll use blue. We get something there, left and down one here, left and down one there, 3 and 3 is right here. So now we do get two vectors. And we can look at the area of the parallelogram that those two vectors generate. So the first thing we want to do is translate, or maybe first shift our parallelogram. Oops. To the point 0, 0. Then take the absolute value of the determinant of, of the matrix whose columns are our new edges of the parallelogram. Okay, so our area is then equal to the absolute value of the determinant of what matrix? This is 1, 2, and this is 2, 1. So we want 2, 1, 1, 2. An absolute value. So this is the absolute value of 4 minus 1, which is 3. I guess we should say 3 units squared if we want to be really, really careful. Okay, so there's the answer. Which means what? If we carve up, well, whatever, you know what that means. It's the area of this parallelogram. The area of this one, which is the same as the area of the shifted one. So we found the area of our original desired parallelogram. Good, good. Okay, the next thing we might ask in a class on linear algebra is, okay, what about linear transformations? How does applying a linear transformation to the plane, R2, change the area of a shape? Right, so we've got a little picture we should have in our head is, here's a copy of R2, there's our favorite shape, a diamond, I don't know. We're applying some linear transformation to this shape, and we get some funky looking thing over here, and we want to know, how does T impact the change of it? How does T impact the area of this thing? So let's let S be the shape in R2 that we care about. And T is our linear transformation. We want to define T applied to S, or the image of S, as just a set of all images of things that were originally in S. Or in other words, everything over here that came from S. We've got this whole thing is called S, maybe. The solid shape over here, this is T of S. This is where everything in S goes to after we apply T to it point by point by point. Okay. Okay, so let's let T and S be as above. Let A be the standard matrix for T. Then what happens? We want to know the area of T of S. The area of T of S is equal to the absolute value of the determinant of A times the area of S. Okay, so the absolute value of the determinant is telling us how big or small the area of S change, or by what factor does the area of S change. Okay, and better still, this doesn't just work for shapes made out of parallelograms. It works for any shape that can be approximated by parallelograms. So this theorem still holds in sort of like a calculus-like setting. So if we have, not a triangle, which you can build out of parallelograms, but actually like a circle, which you can approximate by parallelograms, approximate by squares even, then we can still get a version of theorem 310 working for us. I'm sorry. We don't want S to be any shape here. I've made a mistake. We want T to be as above. We want let S be a parallelogram. Okay. And then the statement makes more sense. It doesn't just work for parallelograms, it works for anything that can be approximated by parallelograms. So a circle, for example, can be approximated by very small squares, as we've seen in calculus, and we can apply the same arguments to a circle. So let's do just that. Let's let A and B be positive numbers. We want to determine the area of the region E bound by this equation. So this gives us an ellipse. So we've got our copy of R2. We've got, if x1 is A, then this thing is already equal to 1, so this must be 0. So we've got a point at A comma 0, and similarly a point at 0 comma B. and by symmetry over here also, negative a 0 and 0 negative b. So we have this football shaped thing, or this circled like got stretched out in one axis. We want to find the area enclosed by this ellipse. And the smart move is to try and use a little linear algebra to make our life easier. So our solution here is to observe we can make this whole shape the image of some linear transformation. So then, yeah, E, this is our shape E, our solid E. Yeah, so E is the image of D, the disk of radius 1. Under the transformation, what should the transformation be? Right, so we're imagining, what are we imagining? Imagining a little circle over here. And we want, 1, 0 to be mapped to A0 and 0, 1 to be mapped to 0B. So that's telling us everything we need to know. If we want 0, 1, yeah, we want 1, 0 to be taken to A0, and we want 0, 1 to be taken to 0B, then that tells us the linear transformation must have been A0, 0B. Okay, and we know what we know by our theorem, the area of E is equal to the absolute value of the determinant of our linear transformation times the area of D. And so we know what this is AB. We know what the area of the disk of radius 1 is. It's just pi r squared, just pi. And so this is telling us the area of an ellipse without having to do any fancy calculus. No integration involved. Okay, I'll see y'all next time with section 4.1. Take care, everybody.